Oh, I hope you didn't miss me too much in the last 5 minutes. Okay, we did mass spec last week. Today we're gonna do probably what gives you the most, the best information, most of the information for this part, which I remind you is gonna be one of those 25 mark quiz on the exam. So proton NMR and carbon NMR. Today, since we did one workshop and we're gonna do this one now, which is gonna be quite intense, I think I'm gonna do a break. But if you really, really want, and you tell me between proton NMR and carbon NMR, you tell me no, carry on, I will carry on. It's more on you than on me. But proton NMR is probably, I hope you remember enough from Joel's lectures and from, I don't know if you put anything on the exam about NMR, I hope you did. But if you remember, chemical shift, multiplicity, integration, these are the most important parts that you have to look at when you try to solve one of these exercises. And they give you a lot of information about the right structure, the correct structure. So sometimes I keep saying that sometimes even just from proton and carbon, you can guess what the structure is. Starting, of course, from the level, the number of saturation, and even a kind of a good idea of the functional groups. So, for instance, you recognize this one? This is the product that you should have seen by NMR from your green chemistry lab. Now, this will be the clean product. I give you the clean product spectrum, and I ask you interpret it. So, what did you see in the clean NMR spectrum? What do you expect from this proton NMR? Lot of aromatics with a specific multiplicity pattern, some alipatics with also specific multiplicity pattern. So this is the clean spectrum. What do you see? So then I say, okay, one peak, this one is locally different than chloroform, and here this very sharp singlet is is chloroform in CDCl3 because chloroform shouldn't be seen by NMR. Before we start doing some exercise, let's recap. What do you think his peak is? Connected to this one as well in this one. I hope you've done it for the lab report. So this one is a method. Why is a method? It's correct. Okay, let's start from that, which is good. Why is a method? Why do you say this one is a method instead of this one or this one? You should know. Chemical shift. What do you expect the method? It's very shielded or deshielded? Shielded. So it means there's a lot of electrons that are protected. So the more shielded, the more towards zero. The more deshielded, more towards aromatic region, 10 ppm, more or less. So this is the thing. So a very, very important thing you should have a look at whenever you see your exercise for the exam. Look at the proton NMR chemical shift. Where is it? This region, more or less, of the proton, most of the aliphatics. In this region, starting from, let's say, 4, 5, up to 6, you see some double bonds. 7, you see aromatics. So whenever you open your spectrum, you see your proton NMR, you see something around 7, you have aromatics. That also helps when you go to check for, I don't know, on the IR, on the mass spec, to have a look at your structures. Nothing in this region is not aromatic. Then, of course, there are all the in-betweens. Integration. The integration is something also that you really want to see on your example, in your exam or workshop, okay? I don't give you normally on the workshop and the exam, I don't give you the integration as a number. Normally, they give you integration as a sigmoidal, and you need to calculate one according to the other. So you normalize, you say, okay, from my experience, I know that this one weighs 1 or 2. I weigh all the other integrals in proportion. We will see a lot better with examples, and especially at the workshop. Next week, we will have one last lecture on strategy, which is actually a workshop, and then we'll do an assessment workshop on this one to prepare you, okay? But chemical shape is super important to tell you more or less what you have. Integration, it also gives you information about the, sorry, I want to say multiplicity, I meant chemical shape. Then integration to say how many protons of that kind you have, because it's very important, especially if you consider that if there is symmetry, then one weighs maybe double or twice or 2 times or 3 times more than you might expect. This is multiplicity. Multiplicity is doublet, triplet, quartet, that depends on how much and how well one proton sees another proton, which is the next one. So on this one, we say that the methyl group was the one on the far end. If you are not sure, like we did for we just did for the workshop on pericyclic reactions, if you're not sure, place all the protons which are omitted. So here, you have CH3, CH2, CH2. So let's say that this one was the most shielded methyl group is a triplet. Why is a triplet? Next group. Okay, so how do you know it's a triplet? It is itself plus the 2 protons here, that makes it a triplet. Automatically, this one is a quartet. If they are coupled, if the 2 are close enough to see each other, they are coupled for the same reason as this one has 3 equivalent protons, so it counts up 1. It sees 2. No matter if they are symmetrical, it counts 2 plus 1, 3. It makes a triplet. This one, each one of those, 1 is this 3. It has to be a quartet. And then from the distance between the peaks here and the peaks here, you establish the J coupling. So if the J coupling is exactly the same for the 2, you know that the 2 are close enough together. What about this one? This is a singlet. Why is a singlet? Once we establish all these rules, you almost know everything, whatever you need to know for the proton NMR. This one is a singlet because it doesn't have any protons to couple. All the protons from the aromatics are far away, too far away to have an influence on this one. So it's basically isolated. Despite these 2 protons, so you will have, in your spectrum, you will have 1 singlet which integrates 2. And you know that it's a methylene group. They're both methylene groups. So the integration of these 2 has to be exactly the same. But when I give you the sigmoidal integration, you might want to say, okay, maybe this one is a doublet. Maybe this one is 2 protons. So the whole thing makes 2 protons. Has to be equal to this one. This one is 3. If you look at the proportion, when you see next to each other, you can imagine start counting, especially because the first thing that I'm going to give you is CH O, X, N, M, Y, Z, whatever. From that one, from the formula, you can calculate the degree of saturation. And for instance, according to the number of protons, you know that you need to find all the protons in your spectrum. So you have how many protons here? 5, 4, 9, 11, plus 5, 16 protons. You must find the 16 protons in your proton NMR spectrum, so that you can also work out in reverse. So if you know that that one is a thing like integrates 2, you know that one slightly taller in terms of integration might integrate 3. Even if you don't know exactly, you didn't work out exactly the structure of your product, you might guess because you subtract the number of protons. There are exceptions when there are nitrogen protons, so amino groups, or alcohol protons, but that becomes easy as well. So, methyl, methylene, other methylene. This is the aromatic region. Now, when I say that this one doesn't see any of these protons, sometimes it's not true with aromatics because of the ring current. It's called long-range coupling. What do you expect from those? We will analyze single, big by big. But they're not perfect. You see, this is a perfect format. This one is not. This one is not a perfect report. They get distorted a little bit because sometimes 2 triplets come more or less in the same place because one of them maybe is something which is longer than 3 carbons. With the aromatic groups, it happens. It's called long-range coupling. I'm sure Joe told you about that. This is something that maybe you won't see at your exam unless I give you, sometimes I give you a proton NMR, but then an expansion on a specific area. When there is an expansion on a specific area, look at it because it probably gives a lot of information. So this is HA, we discussed, HB, coupled. HC is the singlet. And then on those, you have HD. Which one is HD, you think, on this area? Starting from the left-hand side, middle, and right-hand side. Which one is HD? Look at the nature of these protons. Are all aromatic protons, but some of them are more deshielded than others. Why? Or which one is the most deshielded? Or in this case, the most shielded, probably. HD should integrate 3. So you can guess from the integration as well. Have a look at the size, even roughly, at the size of the integration. This one is smaller than this one, but definitely larger than this one. Why is so deshielded? Because of all the aromatic protons is the one that suffer the least the electronegativity of the neighboring carbons. Then we have HE, is this one, which integrates 2. It's something in between. So this one is close enough to this aromatic ring, which is acting as an electron-withdrawing group, so it's deshielding. Remember, electron-withdrawing group tends to deshield, so put it at highest ppm. But it's not as much as those. Those, remember also the symmetry. This one is symmetric, so these two are different, but they almost overlap. So this one should see this one, it's a singlet, which is another singlet, so it's a doublet. But both of them are doublet and doublet. Actually, it's more than that because of the low range coupling. Basically, those C's also a little bit of that. It is influenced by a little bit of that. But the integration is 4. Because what is true on these two is exactly mirrored on the other side. Okay? So this one, you see a doublet, because this is also only this one. Instead of seeing a doublet, it sees a distorted doublet. Something like that. The other one is affected more by this aromatic ring and a little less by this other one. And it forms another doublet. So basically, it grows as this one. It's very important that you understand the integration for. This is not a difficult one. So if I give you a molecule like that at the exam, you should be able to see it. What I will give you at the exam is this formula from which you can start calculating the number of unsaturations. I'll give you the proton NMR. You'll see also the carbon NMR, then the mass spec as well. So what can you tell me from the mass spec? I'm going to see this one at some point, around 90. You see the loss on one side, but especially you see the whole loss of, remember that the easiest reaction you can do on the mass spec is the same that you will do on bottom flux, so hydrolysis of this ester group. So you will see definitely the loss of the molecular ion and the loss of this fragment. So have a look at the slides that are left for the past lecture and try to compare the two of them. It comes very useful when you do practice. This is if I cancel everything. This is how you should report your spectrum. In this case, of the 500 megas, you write CDCl3. Then there is the delta, which is the chemical shift, and it's a multiplicity because you cannot say it's really a doublet. Eventually, when you see something like that, even if you are in the research group, even if you're publishing a paper, you call it a multiplet, and nobody will complain. It's an apparent doublet, two doublets, but it's not exactly. The same is for this one, it's an apparent triplet, but it's not exactly a triplet. So these extra peaks are not impurities. It's just because of the long range calculus. Then this area comes easier. For instance, this one is a triplet, and there is a J. Integrate straight, and it's HA. This J has to be exactly the same as this one, which we also that. You are not supposed to calculate the J at your exam, but you can have a look. I will give you something which is quite explicit. I will give you quick questions. So if it's something that is coupled with something else, especially if you see a triplet or a quartet, most likely they're coupled together, most likely you have an ethyl group. Or something similar, not necessarily, in this case, an ethyl group, but it could be something which is quite explicit that is coupled, okay? Now, very quickly, evaluating impurities. If you had impure spectrum, you can establish on the same lab report. You can say this is the pure product. These are from the starting material. So for instance, when you have two close to each other on the methyl group, probably one belongs to the product, one belongs to the starting material, which still has this system, but it's shifted, cannot overlap perfectly. So if there is an impurity, you have almost basically double the signal. It's more difficult to you see the boronic acid. But when you have aliphatics and aromatics, they basically double all the signal. They are more or less in the same position, but not exactly. The same is here. The two methylanes. This methylene is more or less in the same position as this one, but just more or less, not exactly. Close enough, but not in the same position. So, for instance, this one is more dish-shielded. Because when you substitute with a phenyl group, this bromide, the extra aromatic group is more electro-withdrawing. So it pushes all the signals a little more towards high ppm. And that's why if you need to choose between the two, which one belongs to the starting material, which one belongs to the product, this is more likely the one from the product, because this aromatic group pushes the signal in this direction compared to a bromine that pushes more in this direction. So for instance, you can evaluate from the integration, the relative integration, you can start calculating. In this case, you had a 75% yield. Now, let's go a little bit in. Now, we use that one, and I really love to use that one because you actually have the product and then the spectrum to evaluate. But let's go for proper exercises. Coupling constants. I left something on the video to discuss in class. For this kind of exercise, we established in the video HT and HB, and I left what is HC, what do we expect to see from HC. You remember, even slightly, what is HA? Can you tell me about the signal of this HA? He has a coupling constant with HT, and he has a coupling constant which is different from HB. Which one is the longest? Focus on HA. Which one is the longest coupling constant? With HB or with HC? Which one of the longest when you talk about cis trans? Cis or trans? Trans, longest coupling constant. With aliphatics, alkenes like that, not exactly aliphatics, but let's say at least not aromatic. The coupling constant is about between 15 and 20 Hertz. The other one coupled with a cis. And the cis is between 8 and 12. So the center of this peak is your trans coupling constant. This one are your cis. What about HB? It has a trans coupling constant, so you expect a long coupling constant, but also you expect to have another signal. So there are always two doublets, but another signal, which is this very, very short. It's called a Geminal coupling constant. When you have a double bond and you have two protons at the end of this bond, the two of them are different one from another because whatever you have on the other side, they suffer from different environments. If they don't, it means that everything else is symmetrical. If everything is symmetrical, then you end up with one signal. We will see a few of them. But in this case, these two are different because of this one. This very short coupling constant is the Geminal one. We left unknown as C, but it's quite easy. C as well, the Geminal one with D, but he also has a cis coupling with A. So it's very similar to this one, but actually the longest between the two signals is a cis coupling constant, which in this case is about 10. You see 10 Hertz, 11 Hertz, they're all in the range of cis coupling constants. And here we have 17 and 17 exactly, because the coupling constant to the trans is slightly longer. Okay, so whenever you say something like that, especially if you zoom on this region, if I zoom on something, I'm basically going to tell you focus on that part, because that helps. If you have something like that, consider, you don't need to remember all the numbers by heart, but at least that a long coupling constant is more trans than cis is useful to remember. So in this case, H aromatic will be the big lump. Normally, whatever if you have a 600, 800 megahertz, you start distinguish between them. If you have 400, 500 megahertz, probably comes with a signal which integrates 5. All these protons are very difficult to distinguish one from another. Then you have HA with the longest coupling, HB, and HC. And this is how you write it. Forget about how to write it here and just if you need for the future, if you need to report a spectrum rather than interpreting the spectrum that I'm going to give you, if you need to report a spectrum like you have in your lab report, you should write in this way. All the informations are important. Let's say that you're doing something in a research lab, in a project, and you have produced a brand new molecule. You're reporting it in a thesis or in a paper. You want to give as many information as possible. So all the informations are useful. Okay, the proton, the different solvent that you use, because sometimes changes the chemical shift, especially changes a little bit depending on certain solvent. The delta is the chemical shift. Integration, multiplicity, assignation. Which of these protons belong to which part? Okay, what about this one? I'll try to make probably the proton one because it gives you so much information, it's going to be longer than the carbon. I'm going to stay a little longer with the proton than with the carbon, but let's focus on the proton now. What do you expect to see from this one? HA and HB. What kind of signal gives you HB and what kind of signal gives you HA? You have two bromides on one carbon and one proton, and on the other side is reverse, two protons but one bromide only. That tells you something already. Which one is more deshielded, HA or HB? A. Why? Simple as that. The more electron-withdrawing groups you have on one next to one proton, the more that proton is deshielded. The opposite is, of course, if you have two aliphatic groups compared to something which doesn't have them, it will be more shielded, so more towards 0 rather than towards 10. So what kind of signal gives you HA? It is its one, itself, and two more. It's a triplet. And the other one gives you HB. One is a triplet, one is a doublet. So, okay, it's very important that these two, if you try to work out, even just having a look at it, if you see a J, a coupling constant, these two must be conjugated one to another, couple, not conjugated, one to another. So it's very important that the J is as similar as possible. But HA is two HBs, which are magnetic equivalent, and you see a triplet. The other one, you see just a doublet. HA, the triplet, is the one that we say is more deshielded. So if you have a spectrum, it should look something like that. So going back to workup and exam, if you have a system like that, these two, even they look coupled. Of course, you try to work out if it's really coupled when you have all the rest of the information from the other spectra. But they look coupled. You can think that these two are one next to the other. A system like a triplet and a doublet most likely is something here which sees two protons. So the integration here should be 1 to 2. Because this one sees two bromides. Okay. I want to cover everything before we do exercises. Do you remember what are distereotopic signals and why some signals are distereotopic? I don't know if Joel covered this part. Maybe he did, I don't know. Does distereotopic protons rings a bell? Or so what are diastereomers? When you have a current center and you have another current center next to it, and instead of having two enantiomers, because one enantiomer belongs to one specific carbon, so that carbon is chiral, it could have an enantiomer. if you have two chiral centers, you have diastereomers. And the two diastereomers are two different products. They might have slightly different, I don't know, running GLC. They might have slightly different melting point or boiling point. They are two different compounds. Instead, two chiral compounds, regarding talking about chemical reactivity and everything, they are exactly the same. Only one concept that has a different alpha, that turns the polarized light in an opposite way. But when you have two chiral centers, you have the possibility of having two different compounds. If you translate that into an NMR as well, it means that if you have one proton and sees these two, ideally it should be accepted. But if the two metals are diastereotopic, it means that if you replace this one with another one, could be, if you replace this one with another one, you could create a chiral center. The signals are the same. If you have two one next to each other, and you substitute one of those with something which gives you two chiral centers, they will be diastereotopics. For instance, these two. Look at HA, B, C, and D. So here, C and D are not equivalent. Because one points in the direction of the two bromides, the other one points in the direction of the two protons. Even if there is free rotation, when they rotate at the same time. So they suffer of the same magnetic field. This one is said, the two of them, HA, proton and bromide and proton are completely mixed. So these two cannot distinguish one magnetic field from the other. In this case, all the signals are the same. In this case, some of the signals are different. We'll see with an easier example. So on this one, for instance, these two protons are diastereotopic. This carbon is chiral. This carbon is not. So this one has four different substituents all around. So this carbon is chiral. This one is not. But in the NMR, works like that. If you substitute this one with any other proton, any other kind of, not proton, but any other kind of group, you create another chiral center here. And in this case, you can create, instead of two chiral molecules, you create two diastereomers. That makes different enough so that by NMR, you see different signals. So for instance, these ones, instead of, if they are not equivalent, each one of those sees this proton and makes a doublet, but sees also the other proton next to it, which normally you don't see. Normally, if you have a methyl group, you have a signal which integrates straight. In this case, you have two signals which integrates one each instead of one signal that integrates two. And this is because of the diastereotopic proton. These two protons are diastereotopic, so they're slightly magnetically different. So this one makes a doublet with this one, but also a doublet with this one. Basically, not exactly different, but with the same kind of proton. And this is the way that you can imagine it. So substituting one of these protons with any group, Z, X, a carbon, or whatever, a phenyl group, whatever, anything which makes that carbon, also the carbon number one chiral, will make two diastereomers. Two diastereomers will produce two different signals. So if you expand on this area, you have these two protons, and this one is, it says 1, 2, 3, two triplets. So it forms a very complex mixture. It's almost two triplets. It looks like a sextet, but it's not. There is no reason why it should be exactly a sextet, but it's very close to a sextet. Instead, these two doublets, and the other one, this one it looks like a triplet. But look at that. There is something we didn't discuss, but I don't know. I'm pretty sure you did in the past. So this one should be exactly the same shape as this one, but probably two of the peaks are overlapped. How can you distinguish? Do you remember how can you distinguish when something is a triplet or is an apparent triplet? There are two things here that tell you that this one cannot be a triplet. Can you tell me why is that? Why this one? Look at it, this one cannot be a triplet, a real triplet. There are two things. That could be good, although there is what is called roof effect, which sometimes distorted a little bit, but it's a sign as well. The J coupling. It should be, if it was a perfect triplet, look at those. They're almost perfect over now. They look exactly the same distance one to another. If it's a real triplet, have a look at the one that I showed you before, a proper triplet. The J coupling between the central peak and the other two is exactly the same distance. Here it's not. You can see immediately it cannot be. This one is probably the consequence of two double doublets, but one of these two peaks perfectly overlapped from another sequence. You are not expect to see that, but if you work out that this one should be a double doublet, you can say this one should be a double doublet. What do you call it? A multiplet. You cannot distinguish exactly. It's not a triplet. You can say apparent triplet sometimes. Because looking at it, it looks like a triplet, but you know it cannot be a triplet. The main reason is the J couple. And the reason is it should be double doublet, double triplet, which basically forms a sextet, I guess. Again, this is the mole view that you can get from the website. This is one proton. This is the other one. You can see that if you rotate this bond, one proton is always closer to the chloride, the other proton is closer to, basically this one is closer to two chlorides, this one is close to a chloride and another aliphatic group. So they become different, they distort. It's like you see double. Questions on that? Because it's one of the least digested part of proton NMR. For instance, this is the result of 2-bromobutane. I'm not going to stay too long. Use it as an example, but basically try to work out on the signal. This one, yeah, should be a sextet. Is not exactly a sextet, but it appears as a sextet. For instance, you can write down, if you're reporting it as a new compound, you can write it down as a sextet, although it's not. Or you can write down even more correctly, a parent sextet. Before doing exercise, let's recap. You can predict where signals should go based on functional groups you have around, which creates protons more or less deshielded. You can have multiple substitution. Remember, is everyone add to the other. So like before you saw two bromides, is double the amount of pushing in one direction. You can interpolate, but it's very good to understand what kind of, if you have, for instance, if you have in your exam, you work out what could be your molecule. It's good that you go back to your spectrum, whatever the spectrum is, could be a mass spec, could be a proton or carbon, and try to convince yourself that this is the right configuration. Chemical shift is very important because it tells you where the functional groups are and if they are shielded or deshielded. The chemical environment also relates to the electronic structure, but it tells you also, for instance, multiplicity. Some things can be predicted. Let's say some things that are a little more difficult to be predicted. Let's say that, for instance, you can imagine long-range coupling with aromatic protons, but you cannot be sure until you see. Maybe in this case, you go in retrospect and say, okay, it's supposed to be a doublet, but it's a distorted doublet. It might be long-range coupling. not immediately when you see the signal, you immediately say this is long range coupling. Let's work out number of sigma, chemical shift, integration of each one, and then eventually multiplication. So, on this one, how many signals do you expect? Remember, play with the symmetry. Symmetry is highly important. So sometimes you expect so many different signals, but if they're all equal, they become one signal. So how many signals you expect from the cyclohexane molecule? One. Are all equivalent. There is a lot of symmetry. It might be in a chair conformation. They're all the same. You cannot distinguish one proton from the other. This one. Despite a carbon-carbon bond. Remember, when we put something like a signal group here, you had all the different couplings, trans coupling, cis coupling, or geminal coupling. If you substitute that signal group with another signal group, everything becomes symmetrical, one signal. This one is one as well, benzene. I'm not gonna say too long because it's the same, only it's aromatic. The integration will be different. What about this aromatic one instead? 2. You have protons here and you have protons there. And you have protons here as well. So there is symmetry in this direction and symmetry in this direction. So this one is aliphatic and it has to go around 4. All those are aromatic, but instead of having multiplicity, different something like doublets, it's symmetrical. So you have 2. One for the aliphatic, one for the aromatic. Integration. Simple as that. This one, we had one signal only. You integrate it as a 12 protons. I have to say that if you get straight away just one signal, the NMR instrument gives you integration 1. Also because of symmetry. You work out because you will have the formula in this case. In this case, I might give you C6H14. If you calculate, no, this one is, sorry, there will be 12. If you calculate the degree of saturations, you will end up with 1 unsaturation because each cycle is 1 unsaturation. But the integration must be 12. And the same is here. You have one signal only. In this case, 12 again. 6. All of them, one signal only, it will give you one signal. So initially the integration will be 1. You are telling me that is 6, 12, or 12. What about this one? There is some equivalency. F4. Easy. Splitting pattern. Singlet, singlet, singlet. Singlet. So we will use this one again because if you substitute anything here, it gives you a pattern which is very easy to spot. And I often use as example, and not everybody saw it. But if there are 2 metal groups, because of the symmetry, 2 signals, 2 signals. When you substitute any of these 2 metals, then the situation changes, and we will see. I'll give you 5 minutes to work out this one. Try to predict your NMR, proton NMR spectrum from this. So remember, question, we will do the strategy lecture and the strategy workshop. But it's very good that you start doing it. You should start from the degree of unsaturation. So if you want, you can start numbering and counting the number of carbons, protons, and etc., and to understand what you have in class, in at the workshop or at the exam. But in this case, I am giving you the structure. You don't need to do that. In this case, you just need to tell me what is the pattern. So thing you want to check on the NMR, chemical shifts. What are, how many signals? This is very important for the strategy. I really would like you to focus on that. For proton and carbon, you need to tell me first how many chemical environments you have. So how many signals you have for the proton and NMR, how many, the number of carbons you see from the carbon-13 NMR. This is very important. Then you can think about integration. Then you can think about multiplicity. This one should be pretty easy. It will go a little more difficult then. So on this one, we have this dash butyl. How many signals you see? One signal. One signal. They are all equivalent. This bromide is not a proton, so you don't see it. If it was a proton or something else with a proton, then you would see different signals. Here, one signal only. What about this one? Two signals. Then you say, okay, splitting pattern. What is the multiplicity of one to the other? Okay, you see two signals. Two singlet, triplet and quartet, not two singlet. They are close enough to see each other. This one sees itself plus two. They are not anisotropy. So it must be a triplet. This one instead, each one of those, so integrates two. It sees three of the other. Itself plus three quartet. What about this one? This is slightly more complicated. How many signals? Three. So it's completely unsymmetrical. So don't expect any help from symmetry. What is the multiplicity? This one is a triplet. Itself, same as that. What about this one? Sextet, or if they're undecided, when you think is much more than that, you can just call it a multiplex. It could be complex, but a sextet will do. This one, 1 plus 2, and triplet. What about that? If you're not sure, when you see it like that, again, expand it. It's tetrahedral. Put it in a shape that is more familiar to you, if you need to. How many signals? Two signals. Two metal groups and one H. What is the multiplicity of this one? H. This CH here. If you put the proton there or that. Says itself plus 6. So it's going to be a septet or a heptet. I don't remember what it's called exactly from the Latin or not. Oh, this one. Integration 9H, but again, it's one singlet. Probably the machine will give you integration 1. Doesn't matter. This one, 2. We said triplet and quartet. Integration 3 and 2. 3. A triplet. Another triplet. But the signal in between might be complex. It could be a sextet. It could be 1, 4, 6. It could be a sextet, but it could be also slightly distorted. If you say sextet, it's fine with me. This one, 2 signals. One is an heptet or a septet. I don't know. Don't remember what is the exact. The other one instead, each one of the methyl groups are equivalent. So each one of those coupled with one to one, it's a doublet. But the integration is 6. So each of the methyl groups, which are on the isopropyl group, they're equivalent. There is no distinction between one and the other. So if you focus only on one of those plus the other proton, each one of those sees another one, doesn't see, is too far away to see the other methyl group, and anyway is equivalent. So one of those sees a doublet, but that doublet integrates 6. The heptet, which is the most complex signal, actually integrates only 1. So if you have Actually, I can tell you that if you have this kind of system in your exam, you're lucky because you immediately say this is an isopropyl group. Maybe connected with something else, but it's an isopropyl group. More difficult. Again, a couple of minutes to work it out, and you tell me. Stay a little longer on the proton, and then we'll do carbon later on. I want to stay a little longer on the proton because it's the one that actually gives you more information. Carbon 13 gives you a lot of information, but it's relatively easier. The proton could be more complex. So this one, I don't know, we call it a how to work out those. So how many signals from the first one? On this one. How many signals from the first one? 4 signals. What about the second? Okay, then we'll see the multiplicity. What about the other one, the last one? This is more complicated because some of them overlap. We'll say for sure 4, but it could be 3, depending on the NEMAR as well. But 3 at least, if you consider all of those, which might come as a multiplet. And that depends also on the resolution, the power of the instrument you're using. But this one 4, you have one complex mixer, which is the CH here. This is a complex mixer. You will never get, unless you go for maybe a 800 megahertz, you will never see exactly a perfect pattern on that one. Let's stay on this one a little more. So that's the complex mixture which integrates 1. You have another complex mixture which integrates 2. Which one is it? The only methylene you have. This is 1 which is already a complex mixture. So when something complex coupled with something which doesn't have a single proton, if it was complex, it's going to be complex also that one. So if this one is a complex mixture, this one is coupled with this one, and this CH2 coupled also with the CH3. But it has to be a complex mixture as well. And then you have a triplet for this one. Okay. Now this one, we said 2. Are ASC the same signal? Are we okay with ASC are exactly the same signal? So the one in between, this one should be a perfect quintet. Because this here is CH2 and this CH2. So 1 each, 1, 3, and 5. This one should be a perfect quintet. And this one, this is only 1 itself plus the one next to it. It should be a perfect triplet. This one is more complex. I think whatever your NMR is, unless again is at 800, 900 megahertz, you'll have three signals because C, D, E, and F, they create a complex mixture of signals. So you will have something like around 7, you will still have something like that. The integration in this case is very important because if you have to do this one, for instance, what kind of signal gives you? What kind of multiplicity? Singlet? We all agree it's a singlet. What about this one? Another singlet. But this one in your spectrum will integrate 3. This one will 3 H. This one will integrate 2. And this one as aromatic will integrate 4. But you should see the splitting. Ideally, you should see the splitting of C, D, E, and F. But they are so this one is an aliphatic group, but has a strong electron-withdrawing group on this side and another strong electron-withdrawing on the other side. So this one is influenced by a methylene, more shielded than this one. Then the methyl group, it comes around 3 on the toluene side because it's very shielded by the presence of this whole aromatic group. So overall, the aromatic protons must be a complex, but you will have something like that which integrates 4. Then at some point, you have 2 singular. The methyl group being the tallest one. Sorry about my pen, but it's always red traced now. I'm getting used to it. But the integration should be this one. 1 singlet integrates 3, 1 singlet integrates 2, 1 singlet, 1 complex multiplet integrates 4. Now let's go for instead what you're gonna see at the exam. So normally I give you something like that and a series of spectra. In this case, we are just considering a proton. In this case, a very simple proton. What you should do is calculating the dB or degree of unsaturation. You remember how to do it? I will put in the last part with the strategy, but normally to calculate the degree of unsaturation, you count times the carbon plus 2. Then you have a series of, depends on what is next to it. I don't know why this pen is. 2C plus 2 plus N. So every nitrogen gives you an extra minus all the H's. Everything is divided by 2. If it helps, oxygen doesn't count in the calculation. So whenever you say oxygen, whatever it is the oxygen. It could be an alcohol, it could be a carbonate. The oxygen doesn't count in the calculation of the degree of unsaturation. So on this one, for instance, if you have 2 carbons, so 16 plus 2 minus 10 divided by 2. How many saturation do you have? 18 minus 10 divided by 2 is 4 unsaturations. 4 unsaturations is something that should sound very familiar to you. You will see when you do exercises. How many saturations are a benzene ring? 4. 3 each double bond, 1 for the cycle. Remember, each cycle counts as an unsaturation. So each aromatic group gives you 4 in saturation. This is very important to remember. Each double bond is 1 plus the cycle. So if you have 4, you can guess that you have an aromatic group, which will come immediately clear because you have something at 7. If you have something at 7 or slightly less or slightly more likely slightly more than slightly less, but it also happens depending on the groups you have around slightly less. But whenever you have this signal in this region, you have an aromatic group, 99.9%. Then you have something aliphatic as well. You calculate your degree of unsaturation. It comes with 4. Okay, it's very symmetrical. Now you know. Now you try to work out what is next. I'm not giving you the integration. I didn't give you the integration before. I give you now. One integrates 6, one integrates 4. Which one integrates 6 and which one 4? You cannot say for sure, but looking at the height of each one, you might say that this one integrates 6, this one integrates 4. Then what do you know? It's very, very symmetrical because there are two singlets. What makes a very, very symmetric situation like that? And you need to place temporal. So you know that you have something like that. And then you need to place substituents around. What makes this one so symmetrical? This one is one singlet. Two groups which are exactly the same here. Because if it's in the other position, if it's in ortho position, if it's in ortho position, this one will never be a singlet. We saw that in the previous one. Only instead of having two methyl group, you have another chloride here, NCl2. But it gives you something different. This one must have groups which are exactly the same. Especially because if you put two methyl groups, you have your signal which integrates 6. You need to put 6 protons, 10 protons in total. If you have this one at 4 and this one at 6, you can work out from the integration. I will give you the S here. If you know that you have 2 signals only, one integrates 6, one integrates 4, you can work out this one almost immediately. How about this one? Start calculating that. We'll do 5 more minutes and then we'll call a break. How to calculate the unsaturation? Remember the chloride will behave like protons, so you subtract. You can substitute each proton with a chloride with a halogen in general. In this case, it's a chloride. But they count like a proton. So it's like, in this case, you have 10 protons instead of 9. They behave in terms of unsaturation, they count like protons. Instead, nitrogen goes the other way around. You add it instead of subtracting. So the formula here should be H10, C8H10. It should sound familiar. How many saturations? How many saturations? 4. 4 unsaturation. Do you have aromatic groups? Yes. So you automatically know that you can place this one and you need to put substituents around. You need to place 9 protons. So you know that you have a benzene ring because of the 4 unsaturations allows a benzene ring and you have a signal of 7. The signal of 7 is a multiplex. It's not a signal like the one before. What about the other two? Even roughly, if you need to place 9 protons, you have 2 different signals, so you know that your aromatic ring must have maximum 4 protons because you must have 2 substituents. So 2 substituents replace 2 protons on the benzene ring. So your aromatic ring has 4 protons. If you place 4 protons on the aromatic ring, how many other protons are the other signals? We need to reach 9. We have 2 singlets. One integrates. You need to place 5 more protons.
CH3 and then a CH2 scale.
Okay. So signals like that, singlet, it means that they are not coupled with anything. If you have a CH3 here, most likely is CH3. If you have 2 protons here, most likely is a CH2 plus something else. On the CH2, the something else is the aromatic ring, plus you need to place a chloride. So this is the molecule that you have seen before. This is the molecule we have seen before. So before we had the molecule, we try to work out the spectrum. Now we have the spectrum and the formula, we try to work out the substitutions around. 2 signals, singlet, it means they're not coupled with anything. But one is integrates 2, one integrates 3. One is a meter, one is something with another, with 2 substituents. Because the meter has 1 benzene ring as a substituent. Then this methylene here has 1 benzene ring plus your chloride. You need to place the chloride. Job done. What about this one? Degree of unsaturation first. Now, for instance, here, you don't see anything in the region 7, or not even 6 and 5. So you might think immediately there is something which is quite saturated, which is not necessarily true, because if you had a carbonate, you will not see the carbonyl on the spectrum, because carbonyl doesn't have, for instance, a ketone don't have a proton. So you don't see it, but you can work it out from the degree of unsaturation. What is the degree of unsaturation of this one? I heard someone say 0. 0. So it's completely aliphatic. So oxygen is not a carbonyl. So what is this oxygen? Potentially a proton. What does this one look like? And this one? We had this molecule, at least similar, on the same pattern. Okay, a triplet. So as a quoted, what is this one? Probably I will call it a multiplet. You cannot distinguish for sure it's a multiplet, but look at the coupling. Do they look coupled to each other? Even if you cannot calculate it fully, do they look coupled to each other? More or less. So what's this one? You need to place 8 protons. What is the integration of each peak? This one is a triplet, which could be triplet on this side. What does it tell you normally? A CH3. So this one should integrate 3. Okay, -5. If you have these 2 coupled, one is 3, the other one is normally 2. What about this one? We're missing these two. Okay, so this one with the bromide. With the OH, the only difference here is that in this case, and this is something that we need to talk about now. This OH. In this case, you see very well the OH group. Which one is the OH group? The same group. So the proton of the OH doesn't couple with anything ever. No matter what, it doesn't couple with anything. But what is important here is that normally, depending on the concentration, you see or you don't see this proton. Sometimes, depending if it's very diluted, it exchanges this proton, exchanges with deuterium, and it disappears. Or all the signals normally, another thing that we can say, all the signals normally, whatever the deuterated solvent, they go in the same area, sometimes with the exact chemical shift. The protons of alcohols and also the protons, I anticipate the protons of amino groups, they're mobile protons. Depending on concentration, they can be in different areas, slightly different. So it's not unlikely that this one might be seen as 6, 7, or sometimes even a 10, depending on the concentration. It's a mobile proton. Sometimes it disappears completely. Normally, at the exam, how do you know? Okay, before telling you about the exam, how do you know in the lab if that is a proton or that kind of mobile proton or not? Normally, what you do in the lab is you add, if you see it and you add some deuterated water and you run the spectrum again, it disappears completely because in this case, it exchanges completely. If you had a signal, you add deuterated water, you run the NMR again, and it disappears, that is an alcohol. Full stop. If it's an amino group, that is an amino group. Normally, you will find in most of the exercise like that, I would say, is it exchanges with deuterated water. If I tell you, if there is a zoom on a particular region of the spectrum, which you see these protons, and I say that that one exchanges with deuterated water, either is an alcohol or is an amino group, or is a proton of an amino group, of course. That's very important because it's useful. Or this one, in this case, could be propanol. Shall we do a break? We'll carry on then. We'll do quickly a couple of more exercises on proton, and then we do a carbon, or you prefer me to finish completely the proton? We have a break and then we do carbon 13. Who wants a break? Nobody? You're great, guys. Okay, let's carry on. I'm telling you for you. For me, I can carry on. I have fun with this stuff. I'm a nerd. I have fun with this stuff. So when I have this kind of exercise, like the one that you're gonna see for the workshop or for the exam, to me, it's like a puzzle. I love doing this kind of stuff. I love trying to solve this mystery. So I can carry on the whole day. So you're bad. Okay, this one. Quickly. The chemical saturation, and if we want a break, we'll do a break. If we don't do a break, let's focus. I hope now it can become, you'll become quicker on this kind of stuff. I hope. So CH, C4H9Br. What's the degree of unsaturation? I didn't hear. Can you have a -1? The minimum you can have is 0 storage. Halogen counts like, so it looks like if you're doing, or, oh, I hate this stuff. 4 C4H10. This one will be 4 by 2, so C, 2 minus H divided by 2. 2C, 8 plus 2 minus 10 divided by 2. Minus 10 is 0, divided by 2 is 0, you have 0. Non-saturations. Okay, so your stuff is all aliphatic. Now, let's start to work out. We have 9 protons to place. This is the problem when everything starts overlapping one to another. It might happen. They have a complex mixture of signals, but it doesn't come from the same proton. It may come from two similar protons which are overlapping. In this case, you leave the proton as is, and you focus on mass spec, carbon-13, and IR to help, to try to work out. We saw this molecule as well. If this one integrates, it's a very complex mixture, but if it integrates more or less one, you have 1 and then 8 more protons to put to place. This one looks like we saw this one already hundreds of times. This one looks like a methyl group. But what about this? This is not one single signal. It could be a complex mixture. Normally, when you have something like that, there are 2 CH2s. They see each other, but they also see something else. This is very, very likely. In this case, you have a CH, CH2, and 2 methyl. Anyway, there are 2 aliphatics. They are so close that they overlap each other, but they belong to different signals. So instead of having a perfect splitting, don't know what happened, perfect splitting, you have this one. In this case, 2 bromobutane. Okay, what about this one? This is the situation that I told you before. If you see it, easy. So first of all, degree of unsaturation. 4. And you have something like that. So what is that for? An aromatic group. What about those? This is a very nice and common signature. Octet integrates 1 and doublet which integrates 6. What is that? We saw it before. If I expand it, this is 1, 2, 3, 4, 5, 6, 7. A perfect octet coupled with a doublet can be only an isopropyl group. So if you place 1, 6, it makes 7. You need to have 5 extra protons to put. They're all aromatic. It must be a mono-substituted benzyl ring. Now, before we do carbon-13, I would like to say something about those as well. We will do it again, but I would like to focus a little bit on mono-substituted, di-substituted. We will see better on the aromatic ring. If you have R and Z, this one cancels normally as a 4 multiplet, for H, which is a multiplet. The R and Z are you have HA and HB. Let's call it like that because we make it symmetrical. So HA is a doublet. HB is a doublet, but they are different. Doublets are different chemically according to the electronegativity of R or Z. Depending on who is the most electronegative. If this one is an electro-withdrawing group, we'll put this one, let's say S75, whereas this one, this proton here, if this one is an aliphatic group or an amino group, let's say very strongly electrodonating, it shields more and it pushes this one around 7. So let's call it 7 and 7.5. But still, when you have, this is a very good hint because we will see more. When you have a system like that and integrate 2 and 2, it's a para-substituted benzyl ring. If instead you have in meta, R and Z, you can still distinguish because you must have a singlet or a sort of singlet. Sometimes this one is a perfect singlet. Sometimes it's a distorted singlet, something like that. Which is not a doublet, but is not also a perfect singlet. That is telling you that probably this one couples slightly with the proton here. It is on its HA. But if you have aromatic groups, you might have, if the two functional groups are in ortho to each other, you have multiplet which integrates 4. Para to each other, you have two perfect, almost, depends on the functionality, but almost always two perfect doublets. Two doublets para-substituted MR on this region around 7. When you have a singlet and another multiplet, you might think, okay, this is a benzyl ring, but it's meta-substituted instead of being either ortho or para. This is something that I would like because it's very important for exercises. Don't want to stop, let's do carbon 13. You're okay? It's 3:30. I will try to do 2 minutes of carbon 13. It's shorter than proton anyway. But stay with me because it's important. Okay. Same thing of carbon 13. The most important thing you need to remember for the exam is how the number of carbons you have in your molecule, in your spectrum. Then you can connect with the number of carbons you have in your molecule because I give you the formula. If you have less carbons than you have in your formula, there is some symmetry around. You cannot have more than the number of carbons that I give you in the formula. If you have more than one carbon, there is some impurity, and this is not going to happen at the exercise. So if you count 7 carbons and you see 7 carbons in the carbon 13, that's it. There is no symmetry. On this one, for instance, propanol, there is symmetry with the carbons. They're all different. One suffers for the environment of the next carbon. There is no difference. It means you have three carbons in the formula, you must get 3 carbons in the spectrum. The other thing that we can see on the carbon 13 that we couldn't see at all in the proton is carbonyls. Because you can see carbonyls and carbon 13. You can see them very well. Where do you see carbonyls? If you have the idea that you have a carbonyl, which other spectroscopy you want to see? You want to check? IR. You look at IR, it looks like you have a carbonyl. You go here, you see something between 170 and 200. Depends, it could be 160 as well, depending on what is around the ester group. The ester groups normally are more closer to 160 than to 170, 180. Carbonyls of the ketones are normally between 190 and 200. So depending on where is the signal of the carbonyl, you can already defined if it's a ketone, if it's a ester, if it's an aldehyde, because also aldehyde go very close to 200. In this case, this is something around 170. It shows you it's an ester. You look for the AR, you look for the carbonate. Also from the AR, you can try to work out where is your carbonate, and you get it. Apart from that, how many carbons? 3 different carbons, 3 different signals. What you can talk a lot about everything on the proton NMR, but you can really see on the carbon 13 is the number of carbons and the position. So the chemical shift of where the signal is super important. Between 0 and 30, you find aliphatics. 30, 50, you start seeing some aliphatics, but maybe quaternary carbons. If you move towards 70, 80, 100, you start having double bonds. For instance, all the double bonds of the aromatic groups are between 110 and 140. That depends on what other substituents you have around. There are tables for that, so don't worry, you don't need to remember all of them. But they are very well-defined regions. Aliphatics, whatever they are, this area, between 0 and let's say 40, considering also the quaternary carbons. This area, you have double bonds. This area, you start having carbonate groups. Depending on the substituent, something goes in these other gray areas, but very likely you don't see much between 120 and 140, or between 80 and 60. It's very difficult to see something really meaningful. Symmetry in the carbon 13 is as important as for proton NMR. So, for instance, we saw this one as a proton NMR, and we say it was a singlet. Well, actually, in this one, because you have the weight, it could be two singlets, one for the proton and one for the whole amount of metal groups. What about the carbon? How many carbons do you see? How many signals you expect from this one? 2 signals. One for the quaternary, which normally are very short compared to the others, and one very, very tall for our metal groups. When you see a triplet like that, so no, it's not a triplet, but you have three singlets, normally this one is solvent. In this case, it's deuterated chloroform. It gives you this pattern. So discard it. It's not part of your molecule. But not at the exam, you will see this one is solvent. If I forget, those 3 signals around 77, that's deuterated chloroform. So forget it. What about this one? Count the number of carbons and tell me if you see any symmetry, how many carbons you expect from this one. This is very peculiar already. It is more than that. Sometimes happens that I give you an expansion on that one. If I give you an expansion because there are 2 clues, but in the original spectrum you don't see, I'm telling you that around this region it's actually 2. 1, 2, 3, 4, 5, 6, and 7. This one is the deuterated chloroform. So this is very unsymmetrical. We'll do more exercise, don't worry. Play with that. Give you 5 minutes to play with that. 5 minutes, 2 minutes. Depends how quick are you. Try to work out all the different number of carbons, especially have a very good look at the symmetry. It's very important because when you see your formula on the exercise, you count the number of carbons and you find that there are less carbons in the carbon 13 spectrum, less carbons than you might expect. You can imagine that there is some symmetry somewhere, and that is a good hint. Then you go look at the proton. I try to work out the structure. Because my exercise is always going to be, I give you the spectrum, the spectra, and you tell me the structure. Never I give you the structure, you tell me the signals. at the exam is going to be, please assign the correct structure. But we have so many different, a huge variation of those. But there is, for certain things, the carbon-13 is easier to interpret because there is a lower variety of things that you should see. For instance, there is not coupling constants. You know why? Do you expect to see coupling constants on the carbon-13? Or you always expect to see singlets? You remember that from the theory of the NMR. You always see singlets on the carbon-13. Why? Because you force it to decouple it from the proton. If you do the normal NMR on carbon-13, you will see, and some people, groups, they do study the mechanism following carbon-13 NMR. Sometimes they don't decouple it. But most likely, if you're doing it as a characterization like I do in my lab, you will see the coupled signals. So whatever could be your strange multiplicity, you decouple from the proton, and you see always singlets. And that means also that they give you something even less than the proton NMR. So despite that one signal it might be taller than another, it does not correlate with quantity. So you cannot integrate. When they are decoupled, you cannot integrate signals from carbon-13. So the first one, how many do you see? 7? Sounds good. What about second one? 6? Can you see symmetry? Yeah. How many signals you expect? Wow. All of them are exactly the same. So you see 6 different carbons, but they're all equivalent, one signal. What about this one? I cannot even count them, but they are basically all different. You don't see too much symmetry. You break the symmetry quite a lot. So I'm pretty sure if you see 17 carbons, you expect 17 signals. Some of them, if you see the proper spectrum on that, some of them probably overlap and they look like you lose symmetry. In this case, I will say, yeah, this is my function. This is actually 2 signals or 3 signals instead of 1. What about the naphthalene? There is good symmetry here. How many signals you expect to see? 4 plus less than 5. So cut in this way, you have 1, 2, 3, and 4, and 5. But then you can cut also in this way because there is symmetry. Now, do remember what you call the different kind of symmetries, but you have a symmetry in vertical and in horizontal. So in actual fact, you see only 3. So if you calculate 1, 2, 3, and 4, 5 on the side, then you should also basically do this one. And it remains only with 1, 2, and 3 signals. What about this one? There is some symmetry, but not the same kind of symmetry. You can break only in half on this side. How many signals do you see? 7 signals. What about this beast? Which I would like you to do it. To produce it in the lab is going to be probably impossible. This one does not exist probably in the Roboto Flask. But on the paper is fun. How many signals you see? 2? Who said 2? So each ring is exactly connected with another methylene group. So the only signal that you see is one of those connected with one of those. Because all the rest is symmetrical. It's mirror one structure to the other. So you actually see, despite it looks like if it's pure, this one you see 2 signals. What about those? We discussed briefly the proton multiplicity of those, and that's really important when you're doing your exercise. What about those? How many signals you see? Ortho, meta, and para. There is some symmetry here. Someone say 4, 4. What about this? What about the metal? The metal is the least symmetrical one. Metal 5. Because some of them eventually are the same, especially these two are equivalent. If there are two metal groups, they are exactly equivalent. The long ring as well, instead of having 6 different ones, these two are symmetrical, these two are symmetrical, but these two are different. So 1, 2, 3, and 4. All the rest is symmetry. What about the para-substituted? How many signals you see from the para-substituted? It's the most symmetrical one, I can tell you. 3. Who said 3? Methyl, okay. But they are the same. 1. Then this quaternary one. Then this one, all the rest symmetrical. It's very important that you see something like that, because when you have an idea, what you're going to do at the exam is I combine all the different functional groups. Then you go, for instance, you get them from the mass spec, and then you get them from the IR. You try to work out what functional groups you have, and you put it on one side. I know that they have a carbonyl. I know that they have an amino group, whatever, but I don't know how they are connected. Maybe you have aromatic rings, and you start looking at familiar patterns in the proton NMR. And then what do you do? Carbon 13, you start counting the number of carbons. You especially try and see what you can tell me about chemical shifts, if they are more aliphatic, aromatic, or carbonyls. Altogether, you see that getting the right structure is just making a puzzle. You just need to connect all the different pieces at some point. You put them together, you should have, ideally, because it's easier said than done, but ideally you have the correct structure. Let's do this one quickly, hopefully. Look at A, B, C, and D, and look at the different patterns. Can you match them? Then we'll see something that is going to be super useful in at the exam. If you want to match them, look at structure first. Then you look at the number of signals that you have. The lesser the number of signals, the lower the number of signals, the higher the symmetry. Try to work out which are the most symmetrical ones and try to match them. So look at A. Can you see good symmetry in A? We'll see when you combine all this info all together and you try to work out the structure. You see, it's going to be fun. For me, it's going to be fun. So A is the least symmetrical, probably. All the methyl groups, the terminal methyl groups 1, 2, and 3 are different one from another. That makes this one and this one completely different. These two are similar, but still not the same, because this one has this more aliphatic, this one has a more tertiary carbon. So this one is the least symmetrical. So probably, if you have 8 carbons, this is the one that is the least symmetrical. So this one, for instance, instead of adding a zone here and then this one is 2 weeks. So start counting them and you work it out. At the exam, probably I will give you an expansion. This one is quite symmetrical. This one is more symmetrical because these two are practically equivalent. So compared to this one, these two are practically equivalent. So you see only 7 instead of 8. This one, yeah, apart from the terminal one, there's good symmetry here. And this one even more. Well, not even more because there's an extra metal group So this one is gonna be the fifth one. So this is the most symmetrical one. So can you match it now? So this one is the most symmetrical, only 4 carbons. Then you have D, 5 carbons. This one is 6, and it's actually, you can all see this is 1, 2, 3, 4, 5, 6, 7. So this one is B with 7 carbons. This one will be almost the same, but I'm telling you that this one actually splits into peaks. So it's important because if you see a pattern like that on your example, on your exercise, and you have 8 carbons, you know that it's very, very asymmetrical. And if it's very asymmetrical, you treat it in a different way. Because also the proton is going to be very asymmetrical. Another thing that really, really helps, and I always, almost always at least put at the exam, is the depth. You remember what the depth is? The depth is a 2D. No, it's not a 2D, sorry. If you vary the angle of the magnet, and depending on the angle of the magnet on the NMR, some of the carbons disappear, some of the carbons, depending on what is the angle, go upside down, and some of the others stay exactly where they are. So the first thing you want to do when you have at the exam carbon 13, go for the normal carbon 13. Then normally it's very likely that I'm going to give you of that 135. I put that in the video, so please watch the video as well. So on the depth 135, the methylene groups go upside down, CH2 goes down, CH and CH3 go up. 99% of the time. Otherwise, sometimes depending on the instrument, they go upside down. Methylene up and CH3 and CH down. In all the exercise that I'm gonna give you, CH and CH3 are gonna be up, CH2 on the depth are gonna be down. A very, very important thing on the depth is also, especially on the 135, quaternary carbon disappear. So what do? You get your structure, you get your your carbons. You look at the carbon 13 as it is, not that, and then you go up in the different depths. Each depth, whatever the depth is, especially the one that gives you more information is the 135, the one where you see something upside down. But in any case, also in all the other depths, quaternary carbon disappears. So you don't see the carbonite anymore in the depth. You don't see any other quaternary carbons. It's very important for the carbonite because it gives you good information. If you have the carbonite from the IR and you see from in the carbon 13 here, it must disappear. But if you look at the structure, all the other quaternary, like this one, the quaternary on the depth disappears. All the CH2 go upside down. It doesn't matter if it's a CH2 of a methylene group or a CH2 like here with alkene. They still disappear. So very important when you get carbon 13, number of signals, position of the signals, look for symmetry, look at the depth if I give you a depth, and that tells you CH2, CH3, or CH. And quaternary because they disappear. I think we'll stop here. I have a lot of other exercises that I can give you for home. Please practice. Please practice. We will see when we put everything together in class next week. Okay. Yeah. Take care.